Hey, Chem 12 class. Sorry I can't be there again today. But I wanted to talk a little bit about some more acid and base chemistry, and we're going to talk about the autoionization of water. So I kind of maybe told a little mini lie, and I said that only ions, only ionic compounds will form ions when in water. And I also said that acids and bases will also form ions when they're placed in water. And I also said that covalent things will not produce ions in water. There is one exception, and that's water itself. It'll auto-ionize itself, or in other words, a very small portion of water will turn into ions when it's just left there. So how this happens is that um, you'll have like a couple of water molecules that are in there, and rather than drawing it like this, I'm actually going to draw it like this. So let's say we have two water molecules that are there. Now, I mentioned this before, is that the oxygen is polar negative. This symbol right here just means like the charge or the polarity of it, and this is going to be negative. And this side right here is going to be positive. And again, this side right here is negative, and this side right here is positive. And what happens is that this oxygen right here is so negative that it'll rip this oxygen, this hydrogen from another water molecule. And what happens is that when you have these two water molecules together, is that it'll actually completely rip off that hydrogen and it'll take it for itself. And what does that produce? Well, it produces an OH and an H3O. Okay? So, in other words, you'll have two water molecules come together and it'll produce an H3O plus and an OH minus. Now, not all the water molecules turn into H3O plus and OH minus. In fact, it's a very tiny proportion of them. The concentration of H plus hydrogen ions, or the concentration of free protons in the water, which happens to be the concentration of hydronium ions in the water, will be the concentration of those hydronium ions will be 1 times 10 to the negative 7 at 25 degrees Celsius. So, and the concentration of hydroxide ions in the water will be the same. So it's an equilibrium reaction where not all of the water is turning into hydronium and hydroxide, and not all of the water is staying as water though. So it's only a small proportion is turning into hydronium. And since this is a 1-to-1 ratio, the hydronium or hydrogen ion concentration will always be the same as the hydroxide concentration. And that's what makes water neutral. The reason why water is neutral is because the hydronium is equal to the hydroxide. What a base is when the hydronium is greater than the hydroxide. Or sorry, what an acid is when hydronium is greater than hydroxide, and a base is the opposite, when hydroxide is greater than hydronium. So even though the water is producing hydrogen ions and it's producing hydroxide ions, it's still neutral because the concentrations of hydroxide and hydrogen ions are equal. And we'll talk about this later, but for the people that have already taken pre-calc 12 and have already studied logarithms, if you were to take the negative log of these numbers, especially if you take the negative log of that number, it would come out to 7, which happens to be the pH of water. Okay, but we'll talk more about that in the future. But what I want to take away from this is that water will just naturally ionize itself to a very small proportion, and that number is going to be 1 times 10 to the negative 7 at 25 degrees. And again, that number will change based on what the temperature is. So if the temperature is higher, we'll be producing more hydrogen ions. Okay, so I want to, before you answer this question right here, I want to talk more about that, the autoionization of water. So we kind of said that water, 59 kilojoules turns into H plus, which is the same. If we did 2 waters, it would be H3O plus, plus OH minus, like that. Now at 25 degrees Celsius, so again, this only applies at 25 degrees Celsius, but water, the concentration of H plus is going to equal 1.00 times 10 to the negative 7 molarity. And the concentration of OH minus is also going to be 1.00 times 10 to the negative 7 molarity. So what we're going to do is we're going to make a KEQ expression out of this. Now, if I made a KEQ expression, it would equal the concentration of H plus times the concentration of OH minus, and that's going to be divided by the reactants. Now, the thing is with the reactants is that it's water, and what I should have wrote is that H plus is dissolved in water, so it's aqueous. OH minus is also dissolved in water, so it is also aqueous. You can't have water dissolved in water, so that's actually going to be a liquid. And if you remember from chapter 2, liquids and solids do not go into your KEQ expression. So what is the KEQ of water? Well, the KEQ of water at 25 degrees Celsius is going to be 1.00 times 10 to the negative 7 and times 1.00 times 10 to the negative 7. And that KEQ of water is equal 1.00 times 10 to the negative 14. And that's the KEQ of water. Now, water's a very important thing for solution chemistry, for acid and base chemistry. So instead of calling it KEQ, we actually end up calling it KW. But essentially, it is exactly the same as KEQ. And you can actually find this number on your data sheet that I handed out yesterday. It'll say Ka, or same thing, but it says Ka of water, or KW, we'll call it KW from now on. The KW is 1 times 10 to the negative 14. And all it is the concentration of hydrogen times by the concentration of hydroxide. Okay. Now, why is that important? Is that, let's say if we had like water like this, plus 59 kilojoules, we don't really have to add that stuff in there. And we add H plus plus OH minus like that. So I have my formula right here for water. And then let's imagine that we did something like this. We added a very strong acid. And if you remember our definition from yesterday of what a strong acid is, it means that it's going to 100% ionize. So when we have 1 molar HCl, and again, hydrochloric acid or HCl is a very strong acid, it's going to 100% ionize, and that means that 1 molar HCl, this is the same as writing 1.0 molar H plus or H3O plus, okay, because it's strong. So all of that HCl converts into H plus. Now, essentially, what that means is that for our water, since that acid is dissolved in water, it's going to increase the concentration of H plus. Now, before, the concentration of H plus was 1 times 10 to the negative 7, and we're adding 1 molar HCl. So that is that is a huge increase in H plus. If we were just to add it up, it would be 1 plus 1.00 times 10 to the negative 7, or in other words, it'd be 1.12345, like that big, okay? But the natural H plus that's in water is pretty insignificant compared to the acid that we're adding it to. So what we'd say is that the concentration of H plus is going to be 1.0 molar H plus in there, because it got all of its H pluses from the HCl. So what we can do is we can figure out what is the concentration of everything. So Kw equals H plus times OH minus. We know what the H plus is because we know that this is going to 100% ionize. So we know that the concentration of H plus, since it's 100% ionizing, is 1.0 molarity. Okay. Now we need to figure out what is the concentration of OH minus. Even though it's a strong acid and there's 100% ionization and it's a very strong acid, we're going to be still producing, there will still be hydroxide in the water. It'll be a very low concentration of hydroxide, but there still will be. So we're going to plug in and calculate what is the hydroxide calculation. Because again, if we increased this concentration, then that means it'll be shifting this thing to the left, and it'll decrease the OH concentration. So we know what Kw always is. Kw is going to be 1.00 times 10 to the negative 14. We know that H plus is going to be 1.0 molar because it's 100% ionization. And now we just need to calculate what is the concentration of OH minus. And that's an easy calculation. Divide both sides by 1.0, and we get the concentration of OH minus is equal to 1.0 times 10 to the negative 14. So that is our concentration of OH minus, and that is our concentration of H plus. Now, this is an easy calculation because we're dealing with a strong acid, and strong acids have what am I thinking about? Oh, strong acids have 100% ionization. Should probably edit that out, but I'm not going to. Strong acids have 100% ionization, so we know it's going to be 1.0 molar. If we, in the future, and we are going to do this, we're going to talk about weak acids. So if I talked about 1.0 molar citric acid, now that becomes a much more complex question because we do not know how much H plus 1 molar citric acid is producing. We know how much H plus 1 molar HCl is producing. It produces 100% of it, so it produces 1.0 molar H plus. But once we start dealing with weak, we're going to have to start doing ice tables. Okay, you should be given a practice sheet right now and a worksheet, and I would like you to work on it. I thought there were some questions in the worksheet that you might struggle with, and so you can put the video on pause right here. I got not all the whole worksheet on here, but I will go over the worksheet and certain specific questions that I think you might have questions about. Okay, so put the video on pause, and then once you feel like you're getting stuck, unpause the video, and you can hopefully answer a few of your questions. Okay, so hopefully you've unpaused the video now, and you can. I'm gonna skip to question 8. I felt like 1 through 7 was pretty standard. So given the equation, write down the acid on the left side. So again, this is here's our conjugate pairs right here, this one right here, and this one right here. Now our conjugate acid is going to have one more proton. So the acid on the left side is H2S. The other way you can think of it too is that as H2S turns into HS minus, it's going to lose or donate a proton. And so it loses a proton, and so H2S becomes HS minus. So the base on the left side is going to be this one right here of HCO3 minus, right, like that. Now, again, we know that these ones are conjugates right here. So the acid on the right side has to be the one with an extra proton. The other way you can think of it is this one turns into this one, it has to lose a proton, and losing a proton is the act of an acid. And the base on the right side is HS minus. Okay, I skipped ahead again to 17, 18, 19, 20, 21. So we're going to talk a little bit about these ones right here. So number 17, which would have the higher concentration of acid or hydronium in water? 10 molar HClO4 or 1 molar HClO4? Now, hopefully you can see this. I try to put the whole table on here, but HClO4 is way up here. And we know from this table and the Ka value that it's a strong acid. So we can even calculate what is the H3O concentration in this thing, in this one right here. Well, the H3O concentration is going to be 10 molar. What's the H3O concentration in this one right here? It's going to be 1 molar, since we know that it's 100% ionization. So which one has the higher H3O concentration? Well, it's this one right here, the 10 molar HClO4, or in other words, the 10 molar perchloric acid. Okay. Number 18, what would have the higher H3O concentration in water? 10 molar HClO4, and again, HClO4, I don't know why I erased it, it is right there. And then HNO2 is way down there, nitrous acid. Which one is going to have the higher concentration? We know that this one is going to 100% ionize. So the concentration of H3O plus is going to be 10 molar for this one. What is going to be the H3O plus concentration in nitrous acid? I don't know. Well, we could calculate it. We would have to make an ice table. We would have to use this Ka value, but since it's not 100% ionization, it will be less than 10 molar. Just because of the definition that it's not strong, it's weak, and so it will not produce 10 molar. It'll produce something much less. And you can even see the Ka value is 4.6 times 10 to the negative 4. And so that means it'll be producing a number that is much less than 10. So which one will have a higher concentration? It'll be the perchloric acid again. Okay. Number 19, which would have a higher concentration? HiO3 or H2SO4. So here's HiO3 right here. Okay, we're going to look up H2SO3, sulfurous acid. Sulfurous acid is a weird acid because it actually doesn't form these bonds of H2SO3. It's just SO2 that's kind of living in water and is acidic by nature. And that's why they write this actually right here. So which one has a higher concentration? 1 molar of this or 1 molar of that? Neither one is going to be producing 1 molar H3O plus. They're both going to be producing less than 1 molar H3O plus. But since HiO3 has a higher Ka value right here, or you can just look at the table and be like the relative strength of this, HiO3 is higher. We know it's going to be, that one is going to be producing more H3O plus. What would have the higher H3O plus in water, NH4 or HF? I'll do this in green. HF is right there, and NH4 is somewhere on there. There it is, way down there. So what will be producing more acid in there? The one again with a higher Ka value. So it'll be HF. Okay, which one's the stronger acid? Now this question is a little bit trickier. Now let's take a look at this, and I want to emphasize something right here. This side right here is the acid side. This side is a base side. Now both of these are amphiprotic, so you'll find them on both sides. But if you want to know which one is the stronger acid, you need to look at just the acid side. So I'm going to show you like a very common mistake that people make. So first off, I'll do the question right, I guess. Well, actually, you know what? I'll show you a common mistake that a lot of people will do. Let me pick purple. So they're looking for these HSO3 or this HC2O4, and they'll go like, oh, here's HC2O4 right there. Okay, and they'll look for HSO3, and they might go like, there's HSO3 right there, and they might think that, hey, HC2O4 is stronger, it's higher up. This is on the base side. So remember, this one right here is on the base side. So you're comparing a base and an acid. You can't do that. You need to compare just acids with acids. Here's another HSO3 right here. Okay, but these two right here cannot be compared for which one's the stronger acid. You can compare these ones or which one's the stronger base, and you could say HSO3 minus is the stronger base, but you should be looking at the if you want to know which one's the stronger acid, you should be looking at the acid side. And that's a very common mistake. So we find this one right here, it's the same thing, it's just on the acid side, okay, because they're amphiprotic. They can act as an acid and they can act as a base. So we found HSO3 minus and HC2O4 minus on the acid sides. Now we can compare which one is stronger, and it's pretty clear that this one right here is the stronger one. But if you want to compare, if I ask you which one's the stronger base, well, the stronger base would be HSO3 right there. Okay. Okay. What is the OH minus in a solution made by adding 0.060 moles of calcium oxide to 500 mils of water? And it says be careful. This is one that is a little bit tricky. This requires some Science 10 knowledge on how metal oxides behave in water. And we'll talk a little bit more about this as well. But if you remember way back from Science 10, if you had me for Science 10, I still talk about metal oxides and non-metal oxides in water. And metal oxides produce bases in water, like the Arrhenius definition of bases. So let's take a look at when you have metal oxide and what happens when you put it into water. So here's calcium oxide. Calcium is 2 plus and oxygen is 2 minus. And if you throw that into water, it turns into calcium hydroxide, CaOH2, like that. Okay? Now, the important part to somewhat remember is that if you had, let me kind of reiterate this, the CaOH2, that CaOH2, if you place that in water, it'll produce a Ca2 plus, and I ran out of room because poor planning. If you take that CaOH2 and what's going to happen to it, it's going to produce Ca2 plus, and it's also going to produce 2 OH minuses. And that's why I kind of put there, be careful when you're doing this one, because if this is 0.06 moles, it'll be producing of calcium hydroxide. This will be 0.06 moles. And 0.060 moles. But now look at this. The calcium ions will be producing 0.06 moles. The hydroxide ions, and that's the one that we're really interested in, will be producing double that, 0.120 moles. And that's really important because we want to find out the concentration of hydroxide in there. So the concentration of hydroxide is going to be 0.12 moles divided by our amount of liters. So 0.50 liters. And now we can calculate the concentration of OH minus. Now, metal oxides are strong bases. They will produce they will do 100% ionization as well. And that's why if you looked at the bottom of your thing and you looked at it'll say like an oxide has a very small Ka value, which means a very, very big, a very large Kb value. And we'll talk about Kb values later. But essentially what this question is about metal oxides and non-metal oxides. And we'll talk a little more about that later, but it is a little bit of a grade 10 question mixed with some grade 11 and grade 12 stuff in there as well. So that one's a little bit tricky. Number 29, what is the concentration of H3O plus in a solution made by adding 0.02 moles of nitric acid to 500 mils of water? First off, nitric acid is strong. So when we have nitric acid, it'll be producing that 0.02 moles of nitric acid will be making 0.02 moles of hydronium. And this is what makes working with strong acids a really easy calculation, because it's 100% ionization. So that 0.02 moles of nitric is going to be the same as 0.020 moles of hydronium. Okay, but it doesn't want to know the moles of hydronium. It wants to know the concentration of hydronium. So I just take that, my moles, and divide it by my liters. Okay, so I take my moles divided by liters, my 0.02 divided by my 0.5, and that's just 0.04 molarity. Okay. And then I have this question right here. It's similar to that other question, I think. It says if 0.10 molarity HSO3 is mixed with 0.10 molarity HC2O4 minus, which species, the species means which chemical, will donate a proton? Okay. Now, I haven't taught you this, but I think you can solve it, kind of, maybe. But what we're going to do is first we're going to figure out which one is the stronger acid. So again, we've kind of done this one already, but let's find where HSO3 minus is as an acid. There it is. And we're going to look up for that oxalate ion as well. And I found it. There it is. Okay, so what we know about the hydrogen oxalate ion right here and the hydrogen sulfite ion right there is that the oxalate ion is a stronger acid than the sulfite ion. Okay, so when it comes to these two things, if I'm just going to draw these things out or write them out, might as well start our equation. So we have the hydrogen oxalate, C2O4 minus, plus the HSO3 minus. Now, again, under Bronsted-Lowry, is the definition of the acid is donating a proton. Now, if you have these two things that are competing on which one it's going to donate a proton, and the hydrogen oxalate ion wants to donate a proton, the hydrogen sulfite ion also wants to donate a proton. Now, which one is better at donating protons? In other words, which one is stronger? Well, this one is the one that is stronger. So it'll be the one that donates the proton. So what will happen is that you'll have HC2O4 minus plus HSO3 minus. Now, here's the interesting thing, and it'll always work out this way. So the hydrogen oxalate ion is better at losing a proton than the sulfite ion. Now, if we take another look at this table, the sulfite ion right here, and here's the oxalate ion right there, and then this one right here, the sulfite ion, is better at accepting protons. So what we can say is this one is better at donating, and this one's better at accepting. And so what happens is that this one right here is going to be your acid, because it is a stronger acid. HSO3 minus is actually a stronger base. So it's going to act like the base. What are these things going to turn into? Well, since HC2O4 minus is a stronger acid, it's a better donator. So it donates and turns into the oxalate ion, that C2O4 minus. Now, if you just can't like memorize it, well, since you chose this one right here as your stronger acid, what's it going to turn into? Just look at the table. It turns into that, C2O4 2 minus. Since this one is HSO3 minus is the stronger base, what is it going to turn into? It's going to turn into H2SO3. Like that. So to answer the question more directly, which species will donate? This one's the donator. Okay, HSO3 minus is the acceptor. So hopefully that makes sense. I try to pick out some of the questions that you might have had difficulties with, and or maybe you didn't quite understand. That's how you answer those particular ones right there. Okay.